What if the very first oceans on Earth were not blue at all, but purple? Long before fish, before plants, before anything with eyes, Earth was a young, raw planet. Around 3 billion years ago, the oceans were full of simple microbes, and some scientists think a few of them used a purple pigment to catch sunlight, not the green one plants use today. This matters now, because scientists searching for life on other planets need to know what colors a living world can show through a telescope. Our story begins about 3.5 billion years ago, when Earth's air had very little oxygen, and the sun looked fainter in the sky. In this world, scientists propose that early microbes may have used a molecule called retinal instead of chlorophyll to turn sunlight into energy. Retinal reflects purple and red light, so if these microbes covered large parts of the ocean surface, the water itself may have taken on a purple or pink tint. Later, around 2.4 billion years ago, a huge shift happened, known as the Great Oxidation Event. When oxygen levels in the air rose sharply, many scientists believe this rise happened because green, chlorophyll-based microbes slowly outcompeted the purple ones, since chlorophyll captures sunlight more efficiently. Over millions of years, green life may have spread, oxygen built up, and the ocean's color slowly shifted toward the blue-green we know today. What would you notice first, standing on that ancient shore? By the time complex life appeared, hundreds of millions of years later, the purple period was long gone, buried in rock and time. Today, we only find hints of it in certain modern microbes, called Halobacteria, that still use retinal and still tint salty ponds pink or purple in places like Australia and Senegal. These modern organisms are not the ancient ones, but scientists study them as living clues to what may have happened billions of years ago. Purple Earth hypothesis was formally proposed by scientists Shiladitya Das Sarma and Edward Schwieterman, suggesting ancient microbes may have used retinal-based pigments before chlorophyll became common. This is presented as a hypothesis, not a proven fact, and the researchers themselves describe it as a plausible model, not a confirmed history. Modern Halobacteria, tiny salt-loving microbes, are confirmed to use a retinal-based molecule called bacteriorhodopsin to capture sunlight, and this is well documented in microbiology. These microbes are alive today in salt flats and lagoons, and their pink-purple color is directly observed, not disputed. Geologists confirmed that Earth's atmosphere had very little oxygen before about 2.4 billion years ago, based on chemical signals in ancient rocks. This part of the timeline is well supported by physical evidence. What remains unconfirmed is whether purple, retinal-based microbes were actually widespread enough to color the entire ocean surface. Not all scientists agree on how visible or dominant this purple pigment would have been. Some researchers argue that even if retinal-using microbes existed, they may have stayed limited to shallow pools or specific regions, not open oceans. Others point out that we have no direct color sample from a 3 billion-year-old ocean, since water itself leaves no fossil behind. There is also debate about timing. Some models suggest retinal-based life could have appeared earlier than chlorophyll-based life, while other scientists think both may have evolved around the same general period, competing from the start. This gap in certainty is honest and normal in early Earth science, since the evidence is billions of years old and very indirect. This story does not involve human tragedy, but it touches something deeply human: our need to understand where we came from. For people who study the origins of life, every small clue about ancient Earth feels personal, like reading a faint, half-erased letter from our planet's own childhood. It reminds us that the world we take for granted, blue skies, blue seas, took a long and uncertain road to look this way. Think of early Earth like a dim room lit by a weak bulb. Chlorophyll is like a wide, efficient solar panel, built for a brighter world, while retinal is more like a simple candle-based sensor, good enough for the dim light of a young sun. If ancient microbes really did dye the ocean purple, it means life's very first solar panels may not have looked anything like a leaf. This idea matters far beyond old rocks. Astronomers scanning distant planets often look for a green tint as a possible sign of plant-like life. But if young planets favor purple pigments first, we may be looking for the wrong color. In that sense, this ancient ocean is not just history. It is a lesson in humility for anyone searching the stars. Here is what we know. Early Earth had very little oxygen, and some modern microbes still use retinal pigments that turn water pink or purple. Here is what we don't know: whether ancient purple microbes ever covered enough of the ocean to change its color on a planetary scale. Now, let's look at where this research is heading next. In the near term, scientists will likely keep studying modern retinal-based microbes to better model how they behave in low-light, low-oxygen conditions. And this research is already ongoing. Some teams may attempt to simulate ancient ocean conditions in labs, testing how far a purple pigment could realistically spread. It is less certain, but possible, that future space telescopes could detect a purple-tinted atmosphere on a distant exoplanet, offering indirect support for this whole idea. Our oceans may not have always been blue, and that single idea quietly reshapes how we imagine life's beginning on this planet.